Welcome to Real Civil YouTube channel. In this video, we are going to see how to design a beam for flexural as per recommendation of IS 1893 2016. Okay, so let's begin. So, yeah, so here we are going to see for we have selected one beam AB. Okay, this is from the building, means this is not a single beam. There is a total frame is there. From that frame we have selected the beam AB, and here we want to design or ductile detailing for flexure as per IS 13920 This is the code we are going to use, or this is the latest revision of the code. So here some preliminary data is there. Width of beam width of beam is 300 mm, depth is 600 mm, clear span is 5000 mm, grade of concrete is AM25 and grade of steel is Fe415. Okay, after analysis, as we know that if you consider a beam and if you apply the load combinations and you do the analysis, then these are the results at the left end. Okay, means suppose this is at end A. This is the maximum shear force, maximum negative bending moment and maximum positive bending moment at end A. Then this is the central portion. Here shear force and bending moment values are given. And then at end B, these are the results. Maximum shear force, negative bending moment and positive bending moment. So these are the results. Values are there. Factored axial force here is 0 kilonewton. Okay, this much data is we will require in order to start the design or ductile detailing. Okay, so first, here we are going to start as per IS 13920 We are going to uh, take the checks. So first check is for axial stress. So let's read the clause first. Requirement of this section shall apply to beams resisting earthquake induced effects, okay, in which the factored axial compressive force or stress does not exceed 0.08 fck. Okay, so I will simplify this in our next slide. Let's complete this reading. Beams in which the factored axial compressive stress exceeds 0.08 fck shall be designed as per requirement of 7. Okay, so let's see in which category we are coming. Here factored axial force given is 0 kilonewton. So what code says, we have to do 0.08 times fck, that is 0.08 into 25. Okay, let me check. Yes, AM25. So whatever value will be coming here, it is surely greater than 0. Okay, as force is 0 means stress is also going to be 0. So what you have to do, you have to just compare this value. Okay, if this value, our stress is coming less than 0.08 fck, our value, if it is coming lesser than 0.08 fck, then we can go with design as a flexural member. Clause 6.1 IS 13920 Now second, check for member size. Now there are three checks basically for member size. First check is beam shall preferably have width to depth means B by D ratio more than 0.3. This is the first condition. Second criteria is beam shall not have width less than 200 mm. That means we have to compare the width here with 200. And third criteria is beam shall not have depth more than one fourth of the clear span. Means depth should be less than one fourth of the clear span. Let's see. Uh, yes, here first I have verified the second condition, that is beam should have width greater than 200 mm. In our case it is 300 mm, hence okay. And this is the 6.1.2 clause. Next, depth of beam. So B by D ratio should be greater than 0.3. We have taken B 300, D 600 and our ratio is 0.5. Hence okay, this is the clause. Now clear span, that is L by D, that is clear span divided by depth should be greater than 4. Means we have put in some different form. You can write in this form also, which is coming out to be 8.33. Hence okay. So all the clauses we are satisfying related to check for member size. Okay. Now next is check for limiting longitudinal reinforcement. Before that, we need to decide the effective depth and cover. Okay, you can assume whatever your assumptions are there. In my case, I have assumed that I have given in this slide. So effective depth for moderate exposure condition and fire resistant for 2 hours with 20 mm diameter, assuming in two layers, means I am assuming that 20 mm in two layers, sorry, on average considering 30 mm clear cover for 25 mm aggregate size, means my clear cover is 30 mm. Okay, so I will directly explain you what is this calculation here. This is the total depth, this is the clear cover. Okay, this is stirrup diameter, this is this 20 mm is upper 20 mm bar and this is lower 20 mm bar, and we know that we go up to center of the bar. Okay, like this we calculate the D up to the center. Okay, so that is coming out to be 532 mm. You can do your own assumption also, there is no problem. Now in longitudinal reinforcement, means this is our beam, this is end A, this is end B, then whatever horizontal reinforcement is there, that horizontal reinforcement is nothing but longitudinal reinforcement. So in this particular clause, they have given the requirement for minimum and maximum reinforcement. Let's see. The longitudinal reinforcement in beam shall be given as below. Okay. Beam shall have at least two 12 mm diameter bars each at the top and bottom face. Means as per ductile detailing, we will require 12 mm diameter bars and that are to be two in both top and bottom. Okay. So at least minimum two bars of 12 mm at the top as well as at the bottom. Okay. Now second condition, minimum longitudinal steel ratio P minimum required on any face at any section is, this is the formula, 0.24 under root fck divided by fy. Fck is in square root, okay, and fy is there below and 24. Now this is the maximum, this is condition related with the minimum, and this condition is related to the maximum. So maximum longitudinal steel ratio provided at any face at any section is 0.025. Let's see how much it is coming out. So first, minimum reinforcement 0.24 root of fck upon fy. This is the formula. We know fck is 25, fy is 415. If you solve this, our answer is 0.29%. For that 0.29%, if we want to find out the AST, we have to multiply 0.29 divided by 100, multiply by width, multiply by D. Therefore, this width is 300 mm, this 532 is the depth. We have just calculated it. So 463 mm is the minimum we have to provide this. Now maximum reinforcement is simple, 2.5% or 0.025. Again, this is the width, this is the depth, and this 100 is because of this percentage sign, 2.5%. So that is coming out to be, here I have calculated 3990 mm square. So maximum is 3990 mm square. So let's see what we are getting. Okay. Now let me go back. Yes. Here you can see, if you consider a beam, you will get maximum negative bending moment, positive bending moment at left end, positive bending moment at center, negative bending moment, positive bending moment at right end. Okay, I will show you only for this particular. Okay, so you can do for the remaining also. Same process. Okay, so this is, now remember, at left end, at left end, negative bending moment minus 369. So we are going to check. Yes. So things to remember. This is the left end and the bending moment is negative 369. Means if you see the bending moment diagram, it's something like this. So negative means here. Means whatever tensile reinforcement is there will be at the top, and compression reinforcement is there will be at the bottom. It is exactly opposite of the center. Okay, because at center tension is at the bottom and compression is at the top, but at the support tension is at the top and compression is at the bottom. Okay, so let's go ahead. Our mu is 369 kilonewton per meter. So let's calculate mu limit. Formula is 0.138 fck bd square, fck 25, b 300, depth is 532. So mu limit is coming out to be 292.92 kilonewton per meter. So if you compare these two values, our mu is greater than mu limit. In this case, we go for doubly reinforced section. In short, I will explain the doubly reinforced design. Okay. In doubly reinforced, first we calculate AST1 by using mu limit. So formula is mu limit divided by 0.87 fy d minus 0.42 xu limit, where xu limit we can calculate by using this formula 0.48 d, where d is the effective depth. Okay, now you have to just put the values of mu limit 0.87, value of fy, d, d into, sorry, 0.42 into xu limit. You will get AST1. For AST2, we will require mu2, and it is very simple to calculate mu2. Mu minus mu limit. Mu is 369, mu limit is 292. We will get mu2 as 76.08. So you have to put mu2 here, as you can see. Now 0.87, Fy is 415, D is 532, and D dash we have already calculated during effective depth. Okay, so AST2 is 454. So this is our AST1, this is our AST2, that is combined we will get AST. Okay, AST1 plus AST2. Let's see, if you add AST1 and AST2, you will get the reinforcement 2364 mm square. Okay, now this is the tensile reinforcement which we are going to provide at the top because it is negative bending moment. Okay, now we have to check this reinforcement with respect to minimum and maximum. Here minimum we have calculated 463, which is greater than, and maximum is 3990. Maximum is 3990. Okay, so this value is between these two. Okay, so we can say hence okay. Now let's see how much steel is there at the bottom face. That is ASC is mu2 upon FSC minus FCC into D minus D dash. We know that FCC is 0.446 FCK, and FSC there is one table, that is, you can refer. You have to take the ratio of D dash upon D and you will get the FSC. Okay, after solving this, we will get ASC as 488.21. 488.21, sorry, mm square. Okay, now again you have to compare this with minimum and maximum reinforcement. So here we can see this value is greater than minimum and less than maximum. So right now we can say it is okay. Right now we can say it is okay, but there is one additional clause is there. There is one additional clause. Let's see what is that clause. Now next clause is 6.2.3. Longitudinal steel, means I have told that horizontal steel at the top and bottom. Longitudinal steel on bottom face of beam, on the bottom face of the beam, framing into column, means suppose this is column. Okay, so the steel which is framing into column, that is at the face of column, shall be at least half the steel on its top face at the same section. Means what? Whatever top steel is there, minimum, or we have to provide 50%, at least 50% here. Okay, so that is the clause. So 2364, here right now we have 2364 mm square still at the top, and right now we have 488.24, 488.24 at the bottom face. Okay, that which is not 50%. Okay, so we have to revise this steel. We have to revise this steel. So as per 6.2.3 AS sorry, ASC must be at least 50% of AST. Hence 2364 divided by 2. So that much amount of steel we are going to place at bottom. Okay, and that will be framing into column. So this steel. Okay. Now similarly, you can calculate for other movements also. I have shown you for one movement at the top, negative. Similarly, you can calculate for other movements also. There are some other two clauses are also there that I am going to tell you, okay, theoretically, and its meaning. So longitudinal steel in beam at any section on top or bottom face shall be at least one-fourth of longitudinal steel provided at the top face of the beam at the face of the column. Let me explain. So longitudinal steel means horizontal steel of the beam in the beam at any section, any section, okay, at any section on top or bottom means at top or bottom face shall be at least one fourth of longitudinal steel provided at the top face of the beam. Means suppose at the top face of the beam, suppose we have provided here x amount of steel and y amount of steel at the other end. Okay, then we have to provide one fourth. Okay, suppose this is the column face and this is the column face. Near this column face at the top, the beam reinforcement is x, at this is y. So you have to see which one is greater, x or y. Okay, suppose y is greater than one fourth of y. Suppose this is 3000 or this is 2000. Then 500 mm square steel is required at top as well as at the bottom at any piece they are explaining. Okay, so this is the clause, slightly difficult, you have to read it once again, you will get clear, or you can comment me, I will explain once again if you are in trouble. Now design sorry now how much reinforcement shall be extended into the column. Okay, so that clause is there, 6.2.5, they are in a row. At an exterior joint means outer column, top and bottom bars of the beam shall be provided with anchorage length beyond the inner face of the column. So this is the inner face, this is the inner face of the column. So you have to insert this beam steel beyond the inner face of the column. How much you have to insert? That is equal to development length of the bar. Okay, so development length of the bar in tension plus 10 times the bar diameter minus the allowance for 90-degree bend. I think it is 8d for 90-degree bend. So that much amount of length you have to insert beyond the face of the column. So that is the clause related to the anchorage length. Okay, so thank you so much for watching the video. I will upload this PDF on my Telegram channel. If you have any doubt, you can ask me, you can comment me. Okay, thank you so much for watching the video. Please like, share, subscribe the Real Civil YouTube channel. Thank you so much.